Hi everyone, today I'm going to be solving Griffiths Problem 6.10. In this problem we deal with an iron rod of length L and a square cross-section given a uniform longitudinal magnetization M that's bent into a circle with a narrow gap. And we're supposed to find the magnetic field at the center of the gap, assuming that the width of the gap is much less than the length of the square side, which is much less than the length of the rod. So, as the hint suggests, we're going to be treating this problem as a superposition of a complete torus, which would be if this gap did not exist, plus a square root with a reversed current. So for the first section, for the torus section, we are going to be imagining that this gap didn't exist. We would be we're going to be dealing with bound currents. So we have the equation K bound equals the magnetization times the n hat vector. But since M is longitudinal and N is normal, they're going to be perpendicular to each other. So the cross product, you're just going to get the magnitude of M. In order to find the magnetic field from this, we're going to be using Ampere's law. With a square Amperian loop going around the torus, where dl is an infinitesimally small length vector along that square, A enclosed is equal to K times L. This is assuming that our L is constant. So we can say that BL equals mu naught times KL. Our L's are going to cancel, and then our B equals mu naught K, and then we said earlier that our K is our M, so then magnetic field equals mu naught times M. Now for the second part, the square part, we basically picture it as a square with the current going like this. We're going to use the equation for the magnetic field around a straight wire, which is B equals negative mu naught I over 4 pi r z hat times cosine of theta 2 minus cosine of theta 1. Now, in this case, our theta 1 and our theta 2, I'm going to draw them right here. This is going to be our theta 1. This is going to be our theta 2. And because this is a square, our theta 1 equals pi over 4, and our theta 2 equals 3 pi over 4, or negative pi over 4, depending on how you want to look at it. Finding the cosine values for those thetas, cosine of theta 1 equals root 2 over 2, cosine of theta 2 equals negative root 2 over 2. So cosine of theta 2 minus cosine of theta 1 equals negative root 2 over 2 minus root 2 over 2, which just equals negative root 2. So now our R value here is going to be A over 2. And then in order to find I, we're going to use the equation I equals integral of K times the perpendicular element of dl. And for a constant surface current, that's just going to be K times delta L perpendicular. And in our problem, K is M and delta L perpendicular is W. So that means that our I equals MW. So plugging all of that into our magnetic field equation, we get that B equals mu naught, our negatives are going to cancel, times MW times root 2 over 4 pi times A over 2. And I'm also going to multiply by a 4 here because we have to do this for all 4 sides of the square. So canceling those 4s and moving that 2 to the top, we get that B of the square, oh, and that's in the z hat direction like we found earlier. So we get that B of the square equals 2 root 2 mu naught mw over pi times a in the z hat direction. So now our total b, we're going to combine them. So we're going to say that b equals that mu naught m, like we found earlier, minus 2 root 2 mu naught mw over pi a, factoring some things and making those back into vector notation, we get that b equals mu naught m times 1 minus 2 root 2 w over pi a.